Okay, so today I'm going to be covering a pretty common chemical equilibrium and solubility question involving KSP, QSP, and some of our solubility knowledge, right? So before I dive into this question, I'm going to review with you guys some of the terminology and what it actually means, right? If you guys just want to get into the question, I'll put a timestamp. But if you want to understand why it works, where it comes from, I guess you should stay tuned, right? So first thing I'll talk about is KSP. What is KSP? So KSP, that is our solubility product constant. Why is it called the product constant, solubility product constant? Like if you remember from your previous lesson, right? We worked with K, and K was a ratio of products over reactants. So if K was a ratio, then why are we calling it a product constant? Well, let's take NaCl, for example, salt. If we dissociate this, right, we get our Na plus aqueous ions and our Cl minus aqueous ions. And K, right, so K was the ratio of our products raised to their stoichiometric coefficients. So this being 1 and this being 1, they're both raised to the power 1. So we don't have to write that, right? So that is equal to the concentration of our products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. So what is our reactant? Well, our reactant is NaCl salt, and it is a solid. We can't have a concentration of a solid. That's not possible. Thus why we leave it like this. And this is a solubility product constant. It is the product of the products, right? These are the products. Our ions are the products. Okay, so what happens as KSP gets greater? So as KSP increases, what happens to the solubility? Well, as we said, KSP is really only dependent on the ions, these guys. So as KSP increases, that means that the amount of ions that we have in our products also increases. And KSP, I forgot to mention, is taken at equilibrium. So we're only looking at these concentrations at equilibrium. This is a perfect point of saturation where the forward rate equals the reverse rate. And I'll talk a little bit more about that a little later in this video. But the greater the KSP is, the more soluble the salt or solid is, right? So as KSP increases, solubility also increases. Why? Okay, so let's say our KSP is 10, right? This is a hypothetical. This is probably never gonna happen because our KSP should always be to a negative power because it's gonna be pretty small. But say it's 10, right? And we have another KSP of 30. So what does this mean? So this means that when we took the product of the products, we ended up getting 10, and this is at equilibrium, versus this KSP, where we took the product of the products, so we multiply these two products, we got a KSP of 30. As you can see, 30 is a lot greater than 10. That means at equilibrium, because this is a ratio over our reactants, but since there's no reactants technically, right, it's just a product. So at equilibrium, we can hold more ions. We are allowed to put more ions to reach equilibrium. So the greater the equilibrium, the less likely a precipitate will form. So a precipitate is just a fancy word for solid. So our KSP here is 10. So say our QSP. So what is QSP? Well, KSP is taken at equilibrium, the point of saturation, and I'll get to that a little bit later. But KSP is that perfect point where no precipitate has formed, but if you add anything more, a precipitate will form or a solid will form. So say QSP equals 11, right? 1 greater than KSP. If QSP equals 11, then that means we have more ions than are allowed at equilibrium. The product that we got was 11, the product constant, the solubility product constant we got was 11. And this QSP can be taken at any moment in the reaction. It is a snapshot. It doesn't matter if we take it in the beginning, the middle, the end. And sometimes your QSP might equal KSP, but that's really unlikely, right? You're taking this at a random moment usually. So because your QSP is greater than our KSP, that means we have too much ions in this solution. So, for example, NaCl solid, that turns into Na plus aqueous and our Cl minus aqueous. So because our QSP is 11, we have too many ions. And because we have too many ions, we know Le Chatelier's principles, I'm just going to write Le Chat, that states that when we have a stress on the system, we have too much of this product, our system will react in the opposite way of the stress. So we're going to get more solid, right? We're going towards the reactant side. So because we have too much of this is going to go here, right? And it's going to increase the amount of solid or precipitate. So the precipitate, there will be an increase in precipitate. So a precipitate will form, right? As this is a lot greater than the amount, well, not a lot greater, just 1 greater in this hypothetical situation, but it's greater than the amount that is required at perfect equilibrium. And this will continue to shift to our solid, creating more precipitate until a new equilibrium is formed. So new equilibrium will be formed. And this equilibrium, we call this saturated. So equilibrium means the same thing, so it is equal to saturated. Okay, so here I have 3 beakers. One's going to be unsaturated, one's going to be saturated, and the last one's going to be supersaturated. So what does saturated mean? Well, say I put some NaCl, right? If I put this into this solution of, if I put this into an unsaturated solution, right? That means that I can place more NaCl and no precipitate will form. So we'll get some Na plus ions and our Cl minus ions. That means that our Q is less than K. So what happens when we are saturated? Okay, so when we're saturated, we have the max amount of Na plus Cl minus, right? That could be in solution. Any more NaCl that I add into this solution, a precipitate will form. If I add even just a little bit, a precipitate will form. And what is saturated also known as? Well, this is also known as equilibrium. This is when the forward rate equals the reverse rate of reaction. So in other terms, when the rate of precipitation is equal to the rate of dissociation, or the rate of ionization is equal to the rate of dissociation of a precipitation. So what does that mean? So NaCl, right? This dissociates into Na plus and our Cl minus ions. So the rate of dissociation, that's this way, or we can say ionization, is equal to the rate of precipitation, the rate that these guys go back into NaCl. So that is equilibrium. That is when the solution is saturated. So what is supersaturated? Well, we're kind of getting there with this previous example. So now I actually add the extra NaCl, right? So we're at equilibrium. We have the max amount, right? And I end up adding some more NaCl into this solution. What happens? Well, because it is supersaturated, a precipitate will form. And let's draw this precipitate in purple. It'll end up at the bottom, right? So if this is solid, a solid will form. Why? Well, we have too many ions. So if we have too many of these ions, right, as I've stated before, because of the Chatlayer's principle, our system is going to shift in the direction of less stress. So the direction of less stress is this direction, and that is a solid, right? We have our solid over here. So because we're going to shift to be solid, we're going to form more solid. And remember, precipitate is a fancy word for solid. It just means solid, right? So when we're supersaturated, K, or let's go from Q. So Q is greater than K. The snapshot that we took at this moment is greater than K. So our Q, we have too many ions in solution. Remember, K is the product constant, and if the product constant from Q is greater than K, we have way too many ions, and that's going to form a solid. And I forgot to mention here, Q is equal to K, right? At perfect equilibrium, the snapshot we managed to take, that being Q, happened to be at the point of equilibrium. So supersaturated, this does not last forever, right? Our reaction is going to want to go back to equilibrium. So eventually, we're going to go this way, right? Back to equilibrium, because these Na and Cl minus ions will want to reduce the stress on the system, and we reach a new equilibrium. But this time, this new equilibrium is going to have some precipitate at the bottom, right? And now we're at a new equilibrium, and we're back to saturated. So supersaturated only exists for a short period of time. Unsaturated is when we're allowed to add more of this solute into solvent, and our solvent typically being water. So, and saturated is the point where we cannot add any more. We're at the perfect point before any precipitate starts forming. So yeah, that's saturation and equilibrium. Okay, so question 47. A student mixes two solutions, 10 milliliters of 0.004 molar lead 2 nitrate and 15 milliliters of 0.25 molar potassium chloride. If the solubility product constant, KSP, for lead 2 chloride, PbCl2, is 1.2 times 10 to the negative 5, will a precipitate form when these two solutions are mixed? So just from looking at this is a very, very small number. So I'm pretty positive that a precipitate will form unless we put a very, very, very small amount of solute into our solvent. But we're going to prove that algebraically, right? So how do we know if a precipitate forms? Well, if you remember from this previous explanation, right, when QSP is greater than K, a precipitate will form. And QSP is taken at any point in the reaction where K is taken at equilibrium. So we're going to solve for QSP. So let me just write, if QSP is greater than KSP, a precipitate will form. So how are we going to find QSP? Well, the first thing I'm going to do is write a balanced net ionic equation for these two solutions that we're mixing. So we have PbNO3, 2 aqueous, plus potassium chloride, aqueous. So what does that form? Okay, so what does that form? Well, we could just do a double replacement reaction, right? But through doing that, you're not really understanding what's going on in this reaction. So if you want, you can just do a double replacement reaction and skip, I don't know, like 30 seconds. But I'm just going to explain what is going on and why this double replacement reaction is happening. So we're putting two solutions into this beaker, right? So we have our PbNO3, 2, and our KCl. We're putting that into here. So in this solution, we're going to have some Pb2+, so lead 2+ ions, cations, we'll have our NO3 minus ions, our potassium, and our chloride ions. So what's going on in this solution, right? When we put into water, these dissociate into their ions. So what's going on? Well, some of these ions are reforming back into their original reactants, right? So these could be going back to this, and this KCl could be going back to this. But some of these ions are also replacing each other, thus a double replacement reaction, right? So this PB, right, it can go with Cl, and this K plus, it will go with NO3. So we'll form two new products, that being our KNO3, so potassium nitrate, both have a plus and a minus charge, so we can just say potassium nitrate, plus our PB Cl2, so lead 2 chloride. And the question kind of spoils which one is going to be the solid, right? It tells us the KSP for lead 2 chloride, but say it didn't. How would we know which one's the solid? Well, obviously you guys are probably going to be given a solubility table, but say you didn't have that. If you just had to infer, the one with the higher charges, right? This is 2 plus, and this is 1 minus, and this is plus, and this is minus. Usually, the one with the higher charges is going to be the precipitate, or less soluble, right? Why? Well, because of the lattice energies. So the higher charges means that these ions on the lattice, that just means the surface of the atom, they're more tightly held together. And the water is what is dissociating these ions, what is dissociating these reactants, right? What's turning it into their ions. So when we add water energy, it's turning these this reactant into its ions. But the more tightly held these guys are together, the more hydration energy or water energy is required to separate them. So based on that knowledge, we can say that PbCl2 is a solid and potassium nitrate is an aqueous. If you do have your solubility rules right, you should know that any nitrate is always going to be aqueous, right? Okay, so what's going on in this solution, right? So we have our potassium and our NO3, right? And now we have our precipitate. This guy's our precipitate. So we're going to have some let's draw this in blue. We're going to have some PbCl2 solid forming probably at the bottom, right? So that's going to be our precipitate, or our possible precipitate. Why? Well, it just depends how much of each we put into solution. For example, a piece of chalk, right? You guys know chalk, board chalk, the stuff you write on the board. If you put the whole piece of chalk into water, barely any of it is going to dissolve. So we say it is a solid. We say a precipitate will form, even though there's still a little bit of that chalk that's going to dissolve, right? There's still going to be a tiny little amount of that chalk that's dissolving. But since the majority of it, like 99% of this chalk is not dissolving, we say it is a precipitate. But say we put that little bit of chalk into this solution. We put a very, very small amount. Well, then it's going to dissolve. And when it dissolves, no precipitate forms. So the question is asking, will a precipitate form? Well, 90% of the times, right? 99% of the times, a precipitate will form, given how small this KSP value is. However, as you can see, we have a very small quantity of lead 2 nitrate and potassium chloride. Given how small these quantities are, there is a chance that the PbCl2, our possible precipitate, does not form. There's a chance that there's no precipitate in solution and it all dissolves. So how are we going to find that? Well, we'll have to test for it algebraically through comparing our QSP to our KSP, right? If our QSP happens to be less than the KSP, then no precipitate will form. We will be unsaturated at that moment. Okay, so now that we have found our precipitate, we can come up with the QSP expression. So so let's first dissociate this precipitate. So PbCl2 solid, that turns into, we got our Pb 2 plus and our Cl minus, and these are both aqueous, so AQ, AQ, and the Cl has a 2 on it. Okay, so QSP, so QSP, just a product constant, right? We don't need the reactants, so that is just Pb 2 plus times Cl minus raised to its stoichiometric coefficient. So that is our QSP. So now we need to find the concentrations of Pb2 plus and Cl2 minus in this solution. We need to find that concentration, or this solution, right? So where are we going to get that? Okay, so where are we going to get these concentrations for our Pb2 plus ions and our Cl minus ions? Well, we know that we mixed two solutions of lead 2 nitrate and KCl, and we're given the molar quantities, right? So we can get the Pb from this solution of PbNO3, and we can get the concentration of our chloride from the KCl, the potassium chloride. So let's start with the Pb concentration. So let's first write a balance equation for lead 2 nitrate. So PbNO3 2, that turns into our Pb2 plus our NO3 minus, right? And we put a 2 here. It does not really matter for this question, as these are spectator ions. They are not important. So we have a stoichiometric ratio of 1, so 1 to 1 with our PbNO3, so our lead 2 nitrate, and our lead ions. So for every lead 2 nitrate, there is one lead that dissolves, there is one lead ion that forms. So therefore, because we have 0.004 molar of lead 2 nitrate, we also have the concentration of Pb2 plus is 0.004 molar. It's the same thing. So you may be thinking that, okay, now we can plug that into here, but we can't just do that yet, right? We're mixing two solutions. So this value is before we mix them, right? We need to find the concentration of our lead 2 ion in solution. So how are we going to do that? Okay, so, well, we know that we have 10 milliliters of this lead 2 nitrate solution. So 10 milliliters is the same as 0. So 10 milliliters equals 0.01 liters. So we know that we have 0.01 liters of this 0.004 molar solution. So 0.004 moles per liter, right, times 0.01 liters. So that leaves us with, 0.004 times 0.01. That leaves us with 4 times 10 to the negative 5 moles of the Pb2 plus. Well, we don't want the moles of this lead 2 ion, right? We want the concentration of it. So we know that when we put this into solution, we're putting it into a new volume. So what is that new volume? Well, we're mixing two solutions, one that is 10 milliliters and one that is 15 milliliters. So 10 plus 15, that is 25 milliliters, and 25 milliliters, so 25 divided by 1,000, that is equal to 0.025 liters. So we know that we have 4.10 4 times 10 to the negative 5 mole of Pb2 plus per 0.025 liters. So this is how much Pb we have in solution and in molarity, right? So 4 times 10 to the negative 5 over 0.025. And we end up with 1.6 times 10 to the negative 3 molar. That's our concentration. So therefore, the concentration of this Pb2 plus in this solution equals 1.6 times 10 to the negative 3 molar. Okay, so I made this a little smaller, so now we can solve for our concentration of our chloride ions. And we essentially just do the exact same thing, except now we're using the KCl, right? So our KCl, that turns into some potassium and chlorine ions, right? And these are both to the 1 coefficient. So we also know that this is a 1-to-1 ratio. So whatever our concentration of our potassium chloride is, that will be the same concentration as our chlorine ions. So 1-to-1, therefore Cl minus, the concentration is, well, we're given 0.25 molar potassium chloride. So that is 0.25 molar. And as we said before, right, that is before we put it into solution. So when we put it into solution, so 0.25 molar, so moles per liter. So moles per liter. And we're using 15 milliliters of this. So let's write over here, 15 milliliters, that equals, so 15 divided by 1,000, 0.015 liters. So we're using 0.015 liters of this 0.25 molar solution. So times 0.015 liters, so 0.25 times 0.015, and we get 3.75 times 10 to the negative 3 moles of Cl minus. Right? We cancel these L's and we're left with moles. But we want the concentrations, and we have the new volume, right? That is just the sum of the two volumes that we added into the solution. So that is 25 milliliters or 0.025 liters. So that's all over 0.025 liters. So that divided by 0.025, and we get a Cl minus concentration equal to 0.015 molar. So now that we have our Cl and our Pb, so our chlorine and our lead ion concentrations, we can finally plug that into our QSP formula. And I'm pretty sure you guys know what we're going to do now, right? So, or where to go from now. So QSP, that equals the concentration of Pb2 plus, so 1.6 times 10 to the negative 3 molar, times 0.15 molar squared. Put that into your calculators. So 1.6 times 10 to the negative 3 times 0.15 to the power of 2. And you end up getting a QSP value of 3.6 times 10 to the negative 5. Okay, so over here I wrote down the KSP value. So as we can see, the QSP is clearly greater than the KSP. And when the QSP is greater than the KSP, that means we have too many ions in solution. And because we have too many of these ions, right? Too many ions, more than the required amount for equilibrium, this over amount of ions is going to make the system shift to the left or to the reactant side as a result of Le Chatelier's principle. And because we're shifting here, we're increasing this, the amount of solid or the amount of precipitate. And this will happen until a new equilibrium form. So to answer the question, will a precipitate form? Yes, a precipitate will form. Why? Well, I just explained. And if you want to say why numerically or algebraically, well, that's because QSP is greater than KSP. Okay, so yeah, that is a in-depth solution to this pretty straightforward question. If you understand the mechanics of everything that's going on, you will be able to solve other questions with ease. So yeah, that's why I made sure that I explained every single step, like, thoroughly. For example, for this step over here, we could have just used the C1V1 equals C2V2 formula. But through using that, you're not really understanding what's going on. But by all means, if you want to use it, use it. It's a lot faster, yeah, for sure. But I just wanted to demonstrate what is going on in this reaction. So yeah, that is question 47 of this chemistry textbook review for chapter 7. Thanks for watching.